Now, let's remind ourselves where we've been. We were talking about pulse speed when last we met, and we found that for transverse pulses, as on a string or a spring or a rope, that speed only depended on the tension and the mass density. In the book, we use this mu symbol, where mu is the mass over the length. Okay? Now, this is what we saw when we had simple harmonic motion. It was, the timing was dependent upon how hard it was to move something, how much inertia there was, and how much restoring force there was. Well, in this case, the restoring force is that tension force, and that measure of how hard it is to speed it up or slow it down, that's the mass density, how much mass there is in a unit of length. Now, you notice that here, I've used the symbol rho. That's the way I was trained. When the book was originally written, it was rho. My co-author, Ron, really wants it to be mu, and so it's mu in the book. You can deal with that. Okay? The formula is this one that will be on the front page of the exam, and it's that formula that you are to use to solve all three of those homework problems that were due today. Let's look at this problem that you just turned in. You have a steel wire that is supporting this heavy block, and we pluck the wire in the middle, and we want to know how long it takes the pulse to reach the ceiling. Now, I've got a question. If I pluck it in the middle, why does that pulse go up instead of down? It goes both ways. Just like when you throw a rock in the pond, the disturbance goes in all directions. In this case, the only direction it can go is up and down. It goes both ways. But we're asked, how long does the pulse that goes up, how long does it take to reach the ceiling? Now, if we knew how fast it was going, this would be an easy problem to solve. Well, we can find out how fast it's going by calculating the mass density. That's the mass over the length. The mass, we're told, is 0.4 kilograms. The length is 0.64 meters. And that's going to give me 0.625 kilograms per meter. Now, the tension we find from a free body diagram. If I draw a free body diagram for this block, I have a gravitational force, and that's going to be, if we take the gravitational field strength to be 9.8, call it 10, that's going to be 1,020 newtons. Now, it's just sitting there with no acceleration, so that means that the only other force, the tension force, by the wire on the block has to be 1,020 newtons. Now, question, is the tension the same all the way through that wire?
No.
Sort of. I mean, no, it's going to be bigger here than it is there because of the weight of the wire itself. But you'll notice that the wire has a really, really small mass compared to the mass of the block. Small enough to be negligible. And that's typically the way we think of these problems, that the mass of the wire itself is important when we're calculating the mass density of the wire, but it's not important when we're finding the tension in the wire. Okay, we assume that the mass of the wire is negligible compared to the block, and so we assume that the tension is pretty much the same all the way throughout. If you were to actually calculate the tension up here, it would be 1,024 newtons. And I'm here to say You know, if I came in here and says, oh, you just inherited $1,020, or you just inherited $1,024, you're the same happy. You're the same happy. Okay? Depending on who died. Okay. Now, if I go in and solve for the velocity, that's going to be 1,020 newtons divided by 0.625 kilograms per meter, and that's going to give me 40 meters per second. Now, once I know the speed, it's very easy to find the time. If I use the definition of the speed, that's how far it travels. In this case, it's up, so I'll use delta y divided by how much time. If I rewrite that, I have the time is equal to how far it travels divided by the speed. That's going to be 0.32. It only goes halfway up the wire, divided by 40 meters per second. And that's going to be 0.008 seconds. See if your neighbor got that answer. If not, slap them. Question, folks, just a second. Why did I know. Oh, good question. If you think of this pulse as an object, like a tennis ball, wouldn't it make sense that one that's going up would move slower than one going down? And that's the thing we're going to find over and over again, and especially in this first tutorial next week, is that these pulses act very, very differently than solid matter. In the case of this pulse, the pulse moves by the pieces of wire moving out of the way and letting it go through. But the pieces of wire, whether the pulse is going up or down, they're moving to the side. And so gravity's not making it harder or easier for either of those pulses, because they're always moving to the side instead of up or down. We're also going to find that when a pulse reaches a boundary, like a wall, it turns around and comes back. But not the way a ball would. If you had a ball that was blue on one side and white on the other, and it came in and hit a wall, well, the white side would be leading the charge coming in, and the blue side would be leading the charge coming out. But what we're going to find is that when a pulse comes in, if it's non-symmetric like that, and hits a wall, that instead of just bouncing back like a solid ball, it actually turns around like a snake and comes away. In the case of a fixed end, it would come away that way, with the leading edge still the leading edge. So these pulses act very different than solid objects. Excellent question, thank you. While we're here, we can also talk about that question that you voted off the island. If we took this same setup to the moon and plugged it again, would it take longer or shorter than 0.008 seconds to reach the ceiling? Longer. And the reason is the mass density doesn't change. The mass is the same on the moon as it is here on Earth. The length of it's the same. It's only the tension that changes. And on the moon, since the gravitational field strength is 1/6 as big, I'm going to end up with a gravitational force that's 1/6 as big, meaning my tension force would be 1/6 as big. If I go into this formula and put something smaller, that's going to make the speed smaller, and it's going to go slower. So it takes longer to get to the top. Sorry?
So because, so how do we know that it's a transverse pulse versus?
Good question. The only kind of pulse you can send on a spring or rope, no, on a string or a rope would be transverse, because you can't get them to bungee. You can get a longitudinal pulse on a spring, but it's not very exciting, and we hardly ever do it. We're going to do it once in tutorial next week, and then stop forever. So whenever we're dealing with a spring, string, or rope, it's going to be a transverse. When we're dealing with longitudinal, since slinkies are hard to find these days, it'll be a sound pulse. Okay? On the exams, that's what I'm promising you. Okay? It'll be a sound pulse if it's longitudinal. It'll be a transverse if it's string, rope, or spring. We also talked about the pulse speed for sound, and what we found was it depended on how hot the air was, and whether it was air or whether it was some other kind of gas. We find that in air, it travels at 343 meters per second at room temperature, and as you heat up the room, it goes a little bit faster, 0.6 meters per second for every 1 degree Celsius that we raise the temperature. The formula that will never be used, that will not be put on the first page of the exam, because I don't want you to use it by mistake, is this one here. I just wanted you to see it once in your life. Okay? I mean, there's things you got to see. The Statue of Liberty, the equation for sound pulses. Okay. This is where I wanted to get to. This is the topic of the day, people. We're going to play a game that you learned in Sesame Street. One of these things is not like the other. I've got two lists here. And the list on the left has something in common. The list on the right has something in common. And the two lists are different from each other. With your neighbor, try to find the commonalities and try to figure out what it is that's different between the left list and the right list. With your neighbor, go. You are talking with your neighbor. Okay, brave soul, raise your hands and explain.
Stuff on the right is stationary.
Stationary, okay. Stuff on the left is, for the most part, moving. What else?
Both have a rhythm just depending on if you are moving or the object is moving.
Okay, so both of them involve a rhythm. Can I call that a repetition? They repeat over and over again?
Cyclical.
Okay, so if I look at the flashing traffic signal, it stays in one place, and flashes in a certain interval of time. If I feel the pulse in your wrist, supposing you have one, it doesn't go anywhere, okay? But it just keeps repeating that pulse over and over again in time. When it stops, call someone. Likewise with everything else. Whereas these things are spread out, okay? Long string of boxcars, pages in a notebook, telephone poles beside a long highway. So these are things that repeat themselves, but not in time, but in space. So what we've got over here are temporal repetitions, repetitions in time at one location. Here, we have repetitions in space at one time. All of these things here, we could take a picture of, a snapshot of, freeze them in time, and there would still be the repetition. My point with this exercise is that waves are both. Waves are both a repetition in space and a repetition in time, and we need to combine both of these attributes to understand a wave. Now, a wave results from a periodic disturbance.
Why is there a newspaper?
I do not know, but I have it on good authority that it's been there for a long time, and maybe it's just to see how long it takes us to notice. Not my newspaper. Okay. Now, if I take this wave machine and just create a single pulse, that single pulse travels down and then it bounces back. The bouncing back we'll deal with in tutorial. But that's just a single pulse. If I send a series of pulses at regular intervals, at regular time intervals, what results is a wave. Okay? Now that wave has many characteristics that we're familiar with. It has the same period as the disturbance that creates it. Folks, I can't say that loud enough or slow enough. You cannot have a wave with a different frequency than the disturbance that is creating it. Okay? You think of this wave as a series of pulses. Well, the same frequency at which you're creating the pulses is going to be the same frequency of the wave itself. Now we can talk about the amplitude of each pulse, how far the medium that's carrying the wave gets away from equilibrium. We can talk about the timing, the period or the frequency, and this is just the same as in simple harmonic motion. This is the new piece, the wavelength. If I look at this wave that I've created, the distance from crest to crest, we call the wavelength. Now if I just send a single pulse down there, well, I can't define a distance from crest to crest because there's only one crest. So a pulse does not have a wavelength, a wave does. And finally, the speed. Folks, it shouldn't surprise you that the speed of a transverse wave is given by this formula right here. And the speed of a longitudinal sound wave is given by this value right here. If a wave is just a series of pulses, well, the wave's going to travel at the same speed that the pulses are traveling. The pulses make up the wave. So this result we derived last time is still good. Now, a repetition in space and time. What I'm going to do is I'm going to set up a wave. I want you to get out your cell phone and use it as a camera to take a picture. Take a picture right now. Okay, too late. I took the picture for you. Okay? By taking the picture, we freeze time. Time is 12 noon, okay? Boom, 12 noon for the whole picture, 12 noon, okay? Now the amplitude is the furthest that any part of the medium gets away from equilibrium, either below in a trough or above in a crest. The wavelength is the distance from crest to crest, or from trough to trough, or you could go from equilibrium to equilibrium if you're careful. You have to go from equilibrium going up to equilibrium going up. If you just go from equilibrium going up to equilibrium going down, you only get half of a wavelength. So it's simpler, and you make fewer mistakes if you go from crest to crest or trough to trough. Okay? Now, I like to think of these wavelengths as boxcars on a train. With a lot of trains, the boxcars are all about the same size, and we call that wavelength lambda. Okay? Now, because that lambda is a wavelength, its units are, well, it's length, so it'd be meters. And counting boxcars is like counting waves. We're going to use that in just a minute to solve one of our problems. Now, suppose instead of freezing time, I freeze position. And I do that by painting this rod right here with a very bright phosphorus paint. And then I put a black light here, and I turn off the lights in the room, but I turn on the black light. So that your eye is drawn to just this one rod right here. You ignore the rest of the machine. And as the wave goes by, what you see is that one rod is going up and down, up and down, up and down, up and down, in simple harmonic motion, okay? Now if I plot that position or displacement away from equilibrium as a function of time, it would go up first and then down and then up, and then I get lazy and I just don't take very many points. Now if I had been more careful and taken more points, I would have gotten something that was sinusoidal, okay? Now again, the furthest we get away from equilibrium, we call the amplitude. In this case, from crest to crest, or from trough to trough, is measured in seconds. So it's the period, the time it takes for that one rod that we were concentrating on to make one complete oscillation. Okay? Now, where in this graph would I find the wavelength? Brave soul, raise your hand. Yes.
The equivalent to the period.
Is it? Because one's measured in seconds and the other's measured in meters.
Not in this case.
The frequency is related to the wavelength.
You add together the amplitude?
Okay. We're going to find a relationship between frequency and wavelength. But just looking at this picture, I cannot, just from this picture, figure out what the wavelength is. It was a trick question. We froze position when we made this graph. We said, only concentrate on that rod there. Ignore all the other rods. And as soon as we ignore the other rods, we lose all the information about that wavelength. My point is that we need both of these graphs. That when we freeze time, we get the amplitude and the wavelength. If we freeze position by following a single piece of the medium, we get the amplitude and the period. We need both in order to describe the wave. This would be the spatial repetition, and this would be the temporal or timing repetition. Now this relationship between the wavelength and the frequency is the main point of what we want to do today. That's where we're going. Question real quick, just to see if we're on the bus. I have a transverse wave that is moving to your right. And we took a snapshot of it and froze time right at noon. Now, on that, this happens to be traveling on a string. On that string, I tied two pieces of ribbon at A and at B. And remember, this wave is moving to the right. I took a picture at noon, and that's what it looks like. If instead of a picture, I had taken a movie, we would see that those pieces of yarn at A and B would be moving. Right at noon, they would be moving. Now the question is, how are they moving? Is A going up and B down, or is A going down and B up? Are they both going down, both going up, or is A going to the left and B going to the right? With your clicker, how would they be moving if this were a movie? People, when you get older, get a job that you just love to do. It makes life so beautiful. I'm the happiest man on the planet. Okay, time's up. Okay. Oh. If this were a democracy, B would be the correct answer. Physics is not a democracy. Okay? Let's solve it. This is a transverse wave that is moving to the right. What that means is that as the wave moves to the right, the individual pieces of the string making up the wave have to move perpendicular to the wave. The wave's moving to the right, so these things have to move either up or down. That means E is, well, it's sick and wrong. Sick and wrong. If you chose E, think that through. Okay? Now, we want to look at the movie. We don't want to be stuck with this snapshot. So we look at the movie. And if we look at the movie, what we see in the next frame, this was the frame that was taken at noon. This is the frame that was taken right after noon. 1/10 of a second after noon. Okay? Because the wave's moving to the right. Now these pieces of yarn can only move up or down. And the yarn has to stay on the string. So that means this point A, where I've tied the yarn, has to move up there. And B has to move down there. So A will move up, B will move down, and the answer is A. Okay? If you got B, you need to reassess your life choices. Okay? Now, remember, it's all about pieces of the string getting out of the way for the pulse as it comes by. As this pulse, which is a trough, goes by, B has to move further away to let it, because it's the hump hasn't reached there, so it has to get further away from equilibrium. Whereas at A, the hump's already gone past, so it's going back towards equilibrium. Does that make it more reasonable?
If you just look at what's in front of the point, it'll show you which direction it's going to go.
Right. Exactly. So, in other words, this is right in front of that point, so it has to go there, because it's all moving that way. Okay, problem with your clicker. If the speed of a wave on a spring remains constant, but the wavelength is somehow decreased, what's that going to do to the period? Now we're getting to this relationship that we were talking about. Is that going to make the period increase, decrease, or stay the same? Assuming the speed of the wave stays the same. Making the wavelength smaller is going to do what to the period? Okay. Get it done. Okay, decrease is the correct answer. These people are fine. Okay. Again, if we use this analogy of the train, it becomes clear what the correct answer is. Both of these trains are moving the same speed, let's say 40 miles an hour. They each represent a wave. The length of the boxcars represents the wavelength. If you're standing between these two trains as they go past you, the period is how long it takes for one boxcar to go past you. And if these boxcars are shorter, and they're both trains are going the same speed, these will get past you quicker. So that means the period is going to decrease. It's going to decrease, and the answer is B. Make sense? Good. Now, here's the guts of it. In 205, there was one equation to rule them all, and in the darkness bind them. It was Newton's second law. When we're dealing with waves, it doesn't matter whether it's moving waves, standing waves, longitudinal waves, transverse waves. We're going to find that all waves satisfy what's called the wave equation. And we're going to derive it very easily right here. We see waves that are rolling onto the beach, and we estimate the wavelength at about 3 meters. You measure the time between wave crests at 0.5 seconds. What is the speed of the waves? Now, you've all played this game. You're standing in the waves up to about here, and when the waves come, you jump up on your toes so that you don't drown. And then you go and you wait for the next wave, and you jump up on your toes so you don't drown. Okay, so you're at B, and the waves are moving to the right. So you just jumped up, and then the crest at A moves over and reaches you at B. How long is it going to take to get to you? Oh, we're told that's half a second. Okay, how far did it have to travel in that half second? Oh, 3 meters. So how fast is it going? That's not rocket science. It's going 3 meters in half a second. Well, that's 6 meters per second. What we just did is we took the wavelength and we divided by the period. Now, folks, that's not the form of the equation that I want you to write down. That's not the form that typically is used. Typically, we use the fact that the frequency is 1 over the period, and so we write the wave equation as the speed of the wave is equal to the wavelength times the frequency. And I'm going to put that up here as the grand high wave equation. Before the semester started, we were in Mazatlan, and I went out into the waves. My wife and my sister-in-law and brother-in-law didn't want to go because it was cold. And I was out there and just having a grand old time. Couldn't see anything because there was a lot of sand being churned up. And all of a sudden, there was just things bumping into my legs. You know, and I just, whoa, just all sorts of things bumping into my legs. And I quickly got out of the water, and as I'm getting out, there's these guys putting up these flags. And the flags are yellow. And when we ask someone about the flags, it says, oh, there's manta rays out there. Manta rays. Really exciting. Okay. Now, folks, this sample problem here is similar to one of your homework problems for Monday. Now, when I say similar, what I mean is the same. I've only changed one number. Okay, so pay attention. We have a transverse wave that's traveling on a string. We paint one little piece of that string green, orange actually, okay? And we find that that little orange piece of string travels a total distance of 12 centimeters up and down in 1/10 of a second. the wavelength of the wave is 1.5 meters. What is the speed of this wave? So let me put the relevant information here. We have the amplitude is 1 centimeter, 0.01 meter. We have that the wavelength is 1.5 meters. And we're told that it moves 12 centimeters in 0.1 seconds, a particle. Now, let's solve this together. There's the wave on the string. The wavelength is from crest to crest, and we've identified one point of the string by painting it orange. Now, as that wave moves to the right by 1/4 wavelength, how far has the particle of string moved? 1 centimeter, the amplitude, 1 centimeter. Well, now it's moved another 1/4 wavelength. How far did it move total from the beginning? 2 centimeters. Now another 1/4 wavelength has passed. What's the total movement? 3 centimeters. And now we've moved 1 full wavelength. How far is the dot moved? 4 centimeters. Okay, so for 1 wavelength, we move the dot 4 centimeters. That dot moves 12 centimeters in 1/10 of a second. Now, if there's 4 centimeters in each wavelength, this is going to be 3 wavelengths in 0.1 second. Is that true? Okay, so how many wavelengths for the dot to move 12 centimeters? The answer would be 3. Everyone on the bus? Okay. What I want, in order to use this wave equation that I didn't actually write, I've got the wavelength, 1.5 meters. What I need is the frequency. If I get 3 whole cycles in 1/10 of a second, how many cycles will happen in a whole second? 30. Yeah, if I get 3 in 1/10 of a second, I get 30 in a whole second. So the frequency is 30, and that's going to give me a wave speed of 45 meters per second. Remember, a hertz is just a per second. And so if I take meters times hertz, that's meters per second. Check that your neighbor followed that, because you're going to have to do that on your homework. Okie dokie doke. We're running out of time, so let's quickly talk about sound waves. Sound is a longitudinal wave, and by that we mean that the motion can be represented with a slinky. If I take a slinky and make a bunch of disturbances, a bunch of pulses, what I end up with is some compressed regions where the slinky is bunched, and some rarefied regions where it's spread out. I can do that with sound with a tube that has a speaker in the end of it. That speaker diaphragm is pushed out and in, out and in. If instead of some rock song, I have a pure tone, a single frequency. I'm trying. Okay? That diaphragm is going to go back and forth with the same period every single time. And that's going to create some compressed regions when the diaphragm goes out, and it's going to form some rarefied regions when it comes back. And those will move out like this. Now you can follow a wavefront, a region where it's compressed, as it moves down the tube. Now that's what we were talking about last day when we drew sound as a bunch of lines. Those were the compressed regions that move at the speed of sound. That's the pulse right there. But if I look at a single molecule, it doesn't go very far from equilibrium. Okay? Not very far at all. So we get something like that. And then those disturbances push your eardrum in and out. Now, I have here a speaker, a bell, if you will, and also a microphone to pick up that sound. If I open the bell jar, can you hear it in front? Okay. Now, on the oscilloscope here, we are registering what's on the microphone. Essentially what sound is being picked up there. When I talk louder, it picks up that. Now, what we're going to do is we're going to pump the air out of this bell jar. And that'll take it off the scale for a while, but then it will auto correct and bring it back on. We got plenty of time. There we go, here it's coming. Notice that the amplitude is much smaller, except when I talk. If we continue to pump the air out of this thing, that'll get flatter and flatter and flatter. The message here is that in outer space, no one can hear you scream. Okay? We need that medium, that air to... Okay, folks, you're still paying me for 2 more minutes. Now, as that sound wave goes down, you're going to have regions of high pressure and low pressure, and then atmospheric pressure. Now, it turns out, and this I find remarkable, that at the high pressure regions for normal sound, it's only like 0.03 pascals above atmospheric. Now, you remember that in everyday life when you're walking around, you are surrounded by air that's at 1 atmosphere. And 1 atmosphere is 101,325 pascals, where a pascal is 1 Newton for each meter squared. That's a fairly large pressure. And yet, your eardrums, healthy ones like you have, can detect little tiny fluctuations in pressure that are only 0.03 pascals. Compared to that, that's like nothing. Your ear is a very, very, very impressive instrument. Don't go to rock concerts. Okay? Okay, let's call it quits.